So a lot of times you can just look at a graph and be like, duh, I see it has an asymptote, right? And so we've got a couple kinds of asymptotes. You've got asymptotes that go vertically, which cause a function to be discontinuous because they run this way and the function cannot travel past that asymptote. You also have asymptotes that run horizontally, which don't prevent discontinuity. They don't prevent continuity, but you can see them. So how do you prove them with a limit? So we're going to talk about both of those because that's what your homework is going to deal with. So let's start with horizontal ones. All right, proving horizontal limits. So this kind of goes back to Cassidy's question earlier. This is going to depend on, is this a multiple choice question or is this a question where you have to show your work? Multiple choice question, you can just pick the number that you know is going to be the horizontal limit. You don't have to go through the work of proving it. But when it's a free response, then you do need to show your work. All right, so to do that, the proof method is always to divide by the highest power of x. Method is to divide by x to the highest power. So whatever the highest power of x present in the problem, divide through by that. All right, so for example, if you're to find the horizontal asymptote to the following function. Okay, so if we've got f of x equals 5x plus 2 over 2x cubed minus 1. So you might look at that and be like, the power on the bottom is bigger, therefore the horizontal asymptote is going to be 0. Okay, if it's a multiple choice question, pick 0 and move on. But if you're asked to prove it, well, why does that work? Why does it work that if the denominator has a higher degree, will the limit produce 0, therefore having a horizontal asymptote? So the proof is in the strategy of dividing through by the highest power of x. Okay, so we're going to take the limit as x approaches infinity, because that's where the horizontal asymptote will appear, is out at infinity. And the highest power of x in this problem is what? X to the third. So we're going to divide 5x by x to the third. We'll divide 2 by x to the third. We'll divide 2x cubed by x to the third. And we'll have negative 1 divided by x to the third. So that's the strategy of your proof. Then you'll reduce. So we're going to write equals limit, because we still are doing algebra and we're approaching infinity, which is where those horizontal asymptotes live. And we'll simplify. So we're going to have 5 over x squared as the reduced value, plus 2 over x cubed over 2 minus 1 over x cubed. And so after I've reduced, now I can substitute infinity. So I'm going to have 5 over infinity squared plus 2 over infinity cubed over 2 minus 1 over infinity cubed. So infinity squared is just a greater infinity, and 5 divided by a great infinity is 0, positive. Infinity cubed is an even greater infinity, so 2 divided by that is also going to be 0, positive. And then we've got 2 minus and 1 divided by infinity cubed. So we end up with 0, more or less, over 2, which are both positive numbers. And so the answer is 0. Therefore, since the limit approaching infinity had a result of 0, there is a horizontal asymptote at 0. Okay, so that's just the proof. a strategy for finding horizontal asymptotes. Hypothetically speaking, suppose the question had started out like this. 5x plus 2 over 2x minus 1. What would that horizontal asymptote be? 5 over 2, right? Because the powers are equal, the degrees are equal, therefore the result is going to be the ratio of the two leading numbers. So again, if you're doing a multiple choice, just pick 5 over 2 and move on. But if they're asking you to prove it, the strategy is still the same. Divide by the highest power of x, which now is only x to the first. Divide each term, take the limit, and you'll prove that it comes out to be 5 over 2. Okay. All right, great. So let's move on to vertical asymptotes. Whoops. I didn't write that correctly, did I? Not proving horizontal limits. Proving horizontal asymptotes. Sorry about that. I just caught my eye just now and I thought, wait a minute, that was not right. Okay, so our second set of examples is proving vertical asymptotes. All right, so if finding a horizontal asymptote relies on the limit approaching infinity, a vertical asymptote relies on a different kind of limit. Okay, this one relies on left and right limits. So it's going to rely on the limit approaching a on the left, and it's going to rely on the limit of a approaching a on the right. And that's how you're going to prove the existence of a vertical asymptote. Well, where are you going to get a from? How do you know what a is? What the value? Are you approaching 1? Are you approaching 5? Like, what's the value of a? All right. And so a comes from the zeros in the denominator. So if the denominator is factorable and has zeros, which would not be part of the domain, okay, so we would say that they are excluded from the domain. Those are the a values that you're going to do. And if there's more than one, you have to do it for each of them. Okay, so let's do an actual question. Okay, we're going to prove the vertical asymptotes for the following function. Excuse me. Okay. X squared minus 4 over x cubed minus 2x squared minus 9x plus 18. All right, looking at the denominator, how many potential asymptotes might there be? There might be 3. No more than 3, but 3 would be the max. And so we want to know, by factoring, where those discontinuities are going to happen, so where those vertical asymptotes will be. So this is going to happen by factoring. So we're going to take our g of x and we're going to factor it. So the numerator is easy, x minus 2, x plus 2. Okay, the denominator. These are kind of fun to factor. Okay, at least I like factoring a cubic. All right, so let's do a little side work on factoring a cubic. X cubed minus 2x squared minus 9x plus 18. All right, to factor a cubic, if you don't remember, you're going to split it down the middle. Separate the first 2 terms from the last 2 terms and just factor the first 2. What could you take out that's common between the first 2? X squared, leaving you with x minus 2. What can you factor out of the back 2? A negative 9, leaving you with x minus 2. And then what could you factor out of both sides? An x minus 2. And if you factor both sides out by an x minus 2, leaving you with x squared minus 9. And you're like, oh, x squared minus 9, I can factor that. Actually, I think I'll do it like this. I'm going to write that as x squared. And then we can do x minus 3, x plus 3. So this was factored into 3 linear factors. So that's done with split factoring. Okay, so that was just my little timeout. And I'm going to come back over to my work. And I've got x minus 2 over, x minus 2 and x minus 3 and x plus 3. And so now I notice that I have a common factor, what? Okay, a common factor of x minus 2. So I can reduce that away. What does that mean for the number of asymptotes that I have? There's 2 asymptotes. What's happening at x minus 2? Because it's still a point of discontinuity, but what kind of discontinuity is it? Just a little hole. Okay, it's just a little pinprick, a little teeny hole right there, but it's not an asymptote. And so my a values are plus or minus 3. So this has 2, I think it has 2 vertical asymptotes. And so I now need to check this to the left and the right of both of them. So that's 4 total limits. So I'm going to be checking the limit as x approaches negative 3 from the left. And I'm going to be checking the limit as x approaches negative 3 from the right. And I'm going to check the limit as x approaches positive 3 from the left. And I'm going to check the limit as x approaches positive 3 from the right of g of x. These are called one-sided limits, left side, right side. We're going to compare what's happening on either side. So that really this is 2 separate things. We'll check the negative 3's and then we'll check the positive 3's. When you check it, use the factored version. Okay, it's easier, okay, to use the factored version. And so I'm going to put negative 3 left into the factored version. So that's negative 3 okay, so I just put negative 3 minus, which is a number that's a tiny bit smaller than negative 3. It's on the left side of negative 3. And I'm putting that into the factored version. When I have negative 3 plus a positive 2, I get negative 1 to the left. In the denominator, get negative 3 minus 3, that's negative 6 minus. And negative 3 plus 3, that's 0 minus. Be careful about your signs. The top is a negative number. What's the bottom? I have negative 6, which is a negative number. I have 0 minus, which is another negative number. Okay, so that turns out to be positive 0. So I have a negative number divided by a positive number. That is infinity, but what kind of infinity? Negative. So what that means is the one-sided limit on the left, that this thing is taking a dive heading straight down to negative infinity at that barrier point at negative 3. So watch your signs on that. Okay, we'll do the same thing with negative 3 plus. So that would be negative 3 plus 2. Negative 3 plus minus 3. Negative 3 plus 3. And so the reverse happens. I get negative 1 plus. I get negative 6 plus. And I get 0 plus. Is the top number negative or positive? Still negative. It has a plus. That doesn't mean it's positive. It means it's on the right side of negative 1, which is still a negative number. The bottom. The -6 plus, is that positive or negative? Okay, the 0 plus, is that positive or negative? So I've got a negative number times a positive number. So what do I end up with? So I've got a negative divided by a negative. Two negatives are positive. Either way, that is a vertical asymptote. Okay? But the vertical asymptote's looking like this. So you have to watch me, right? The vertical asymptote's looking like this. Okay? The left one is heading down. The right one is heading up. Okay? So it's going like this. Sometimes asymptotes do this. They head towards each other and they both head up. Sometimes asymptotes head toward each other and they both head down. Sometimes they head towards each other and they do it that way. All right, but this one, from your direction, your perspective, the left one is approaching and heading down to infinity. The right one is approaching and heading up to infinity. So at -3, we have that kind of a vertical asymptote going. And you do the same thing at +3. Okay, when you plug in +3 to the right and +3 to the left, you do the exact same thing to see what's happening, what's going on those two sides. Okay, so that's going to give me 3 minus plus 2. It's going to give me 3 minus minus 3 and 3 minus plus 3. That's going to give me 5 minus, which is a positive number. It's going to give me 0 minus, which is a negative number. And it's going to give me 6 minus. So I have a positive over 0 negative. Sometimes your mind plays tricks on you, especially when you look at you're like 5 minus is a positive number. We see that minus sign and our brains sometimes like do a little, okay, that 5 minus is a positive number. It just means something smaller than 5. Okay, 0 minus and 6 minus. We're like, ooh, 2 minuses make a positive. No. 0 minus is a negative number. 6 minus is a positive number. It's just smaller than 6. So smaller than 0, smaller than 6. The mixture of that is 0 negative. So we've got negative infinity. And then our last one, 3 plus plus 2, 3 plus minus 3, 3 plus plus 3. So we're looking at 5 plus over 0 plus and 6 plus. So everything is positive, and so positive infinity. And that's the behavior of that asymptote. All right, so those are tougher to prove, or not tougher, just like laborious to prove. So thankfully you don't have to do too many of those in your homework.